This is the textbook for the linear algebra course. I call it Key Ideas and Methods for a First Course. So you are probably a major in the STEM areas. This is a very important course for you to use to solve your science and engineering problems. And just a quick glance, if you go forward, you will see, okay, this is a new book developed based on my many years experiences to benefit the new learners. That means this is their first time learning linear algebra. If you're not a math major, or if you are a math major, this course will cover the essential concepts and meanings and methods. So the contents, list of contents. Okay, so today is the very first lecture. So I'm going to start with certainly chapter 1. And chapter 1 is on systems of linear equations. So first topic is introduction to systems of linear equations. So linear equations, let's start with a very simple case. Suppose you think of a straight line. The straight line has an equation of this form. That is ax plus by equals c, right? For example, ABC are numbers. So if I have 2x minus 3y is 5, right? That represents a line. See, you can, if you want, you can write this into a slope-intercept form. And then you will realize it's a line, because you can write, if I move the 2x, if I subtract 2x from both sides of the equation, right-hand side becomes negative 2x plus 5. Left-hand side, it becomes negative 3y. Then this, if I divide negative 3, so I get divide negative 3. So this equation, right, this is just an alternative form of that equation. So I just to show that equation of this form means a straight line. Straight line in the xy plane. So if you show this, the picture, the slope will be 2/3. The y-intercept will be negative 5/3. So this will tell you some slope, y-intercept. So yeah, but a line sometimes has a slope undefined. For example, if the line is vertical, right, the slope is undefined. So in that case, still the equation is in that form. Think what could be the equation of a vertical line. It's x equals something. right? In this form, that's the equation of vertical line. In that case, that means your y has a coefficient 0. Yeah, there's no no slope, right? So x equals certain constant. So whenever you have an equation of this form, such as y with a coefficient 0, right? That means no y in this equation equals 6, for example. This is a vertical line because this is the same as x equals 3 if I divide 2 from both sides of the equation. So yes, so actually we can represent. That means no matter it's a vertical line or not a vertical line, we can always represent a line in this equation form, straight line. But this equation has only two variables, right? This x and y are the variables in this one equation. A, B, C are constants, are given constants. So if you have such an equation, then you have an equation, we call it a linear equation. So we want to extend the concept of a linear equation to a general case. That is a case involving more than two variables. So then certainly suppose I have three variables and it's possible for me to write an equation of three variables. Let's say x, y, z, three variables. And with the coefficients for these variables. For example, if I have a coefficient and a coefficient here, if I have a coefficient in front of this, and then I can do a combination of three terms together, right? So I can put plus, see, equals a certain number. Let's say, then I have an equation. This is just one example. So of course, you don't have to put parentheses because plus and negative means minus. So we can just simply put a negative. And then I just remove the parentheses, make it cleaner. So you have an equation of three variables. So this equation of three variables, do you notice for each variable we have a coefficient? A coefficient, you see, this is a number, right? This is A, B, C, right? So some number on the right-hand side. So this is a linear equation of three variables. But what if you have 100 variables? How can we represent those variables? A way to represent more variables is the way we can represent the variables systematically. But we will run out of alpha betas like x, y, z, and we have 26. And then how do we represent so many variables? So, and the way to represent more variables is to, for example, if I use letter x, I can say x1, x2, x3, for example, that will represent three different variables. You see, introducing subscript. So I use just one letter and then with different subscripts. I mean the 1, 2, 3, right? So x1, x2, x3. Instead of using x, y, z. So we have three variables. And the same equation, you see this, the above equation can be written as 2 times the first variable minus 3 times second variable plus 6 times third variable is 11. So I want to ask you, the two equations. So this one and this one, are they the same equations? Yeah, they're linear equations of three variables. Although the three variables using different names, but they're exactly the same equation. Yeah, so I want you to recognize the structure. So yes, it's a linear equation. So let's look at another example. So if I have this is not linear because we know you see there's if I rewrite the y, view the variable y as something depending on x, you will see y equals negative x squared minus 1. So it's nonlinear because of that term. And another example. So I just want to show a few nonlinear examples. So here is another one. Sin x minus e to the y equals 5, for example. Do you think it is linear or nonlinear? Nonlinear because this is sin x because of this exponential term. So and I'll give you another example. So if I have negative 7x plus square root of y equals 10. This is also nonlinear. So we can see y because square root of y, nonlinear term. So now we want to give a precise definition. What is linear? So you see three examples that are nonlinear equations because of certain nonlinear terms. And by looking at the linear equations, what are the features? Right, no matter how you are going to represent each variable, the linear equation, each linear equation has these variables and with coefficients. And the right-hand side can be a constant. Okay, so let's give a precise form. So suppose I want to define a linear equation that is a linear equation of n variables. That means n can be 3. That means a linear equation of 3 variables. N can be 2, right? So of n variables. So let me write first x1, x2, x3, etc. So I want to list all these n variables. And all these n variables, remember each variable has a coefficient, right? Those coefficients are constants. So let's put a coefficient. So the coefficient in front of x1, let's call it a1. Coefficient in front of the x2 variable, let's call it a2. just to make it match, right? AN, the notation, you see the coefficient in front of the last variable, xn, is called AN. It's just a notation. So it's easy for us to read. And then all these, the coefficient times variable. So, and then I have total of n terms, n variables, each variable, yeah, there's a term, right, involving a variable. So I have n terms, and on the right-hand side, and there's a constant, could be a constant, let's call it b, a number. So all these coefficients and the right-hand side are constants. And then we see the variables. Okay, so that is a definition. What is definition? Definition means if you see an equation of in this form, then we call it a linear equation. So it's very important. From now on, you know what is a linear equation, because whenever an equation is in that particular form, then it is a linear equation. And if you have a linear equation involving n variables, it is called a linear equation of n variables. So, for example, quickly, see, this is a linear equation of 3 variables. So you have x1, x2, x3, right? That's each term is, yeah, with some coefficient, and there are no nonlinear terms. Yeah. So, okay, so you see some examples, and now we know what is linear, what is nonlinear, because if it's not linear, it is nonlinear. That's a very easy one. So as long as you know what is linear, you know what is nonlinear. So now it's a single equation. Suppose I have more than one equation, then I will have a system of equations. So let's look at this example. And this example, I will show you 2 equations. So the first equation is, okay, the constant coefficient will be 1, 1, as you can see, because there's a 1, right? Although I don't have to write that 1 times the variable is still the variable. So when in the case we have a 1 as a coefficient, you don't have to write it. Okay, the second equation, now I have 2 equations. Each equation involves the same 2 variables. And I have a system of 2 equations. So if we solve the system of 2 equations, what do we mean by solving? That means I want to find x1, x2, the values of the 2 variables, such that the values of x1, x2 will satisfy both equations. Okay, so before I know it, let's, yeah, that is what we mean by solution, right? So in order to find solution, then let's solve. We need to find both x1, x2. The values of those 2 variables. Okay, now the easiest way is to eliminate some variables. And then suppose I label this one. So the first equation, I call it equation 1, equation 2, and then let's do a subtraction. So the second equation minus the first equation. Let's see what happens is that, you see the left-hand side, they have the same quantity. When you do a subtraction, the left-hand side becomes 0. The 5 minus 0 is 5. And what we see after you do the subtraction, the left-hand side becomes 0, right-hand side is 5. And that cannot be true because it's always false, right? This is no matter what values of x1 or x2, it's always a false statement. That means the system cannot have a solution because no matter what value for x1 and for x2, and these two equations imply that 0 is 5. So it's in, it is always false no matter what. So and also you can reduce it if you want to divide both sides of the equation by 5. This is the same as saying 0 equals 1, right? If I divide 5 both sides, right? So that's a 0. Left-hand side is 0, right-hand side is 1. So this 0 equals 5 or 0 equals 1, yeah, they are kind of equivalent. So they, although they look different, but they are saying the same thing. So from one, you can arrive the other statement. So they are equivalent. So that means the system has no solution. Well, it's possible a system has no solution. And let's think of another system. And here is a new system. And the second equation in the system is let's say first, second, right? Here is another example to show you that. What about a new system? This system, if I want to eliminate some variables, let's say we add this time, because by doing addition, we can quickly eliminate x1 variable. So let's simply add two equations. As a result, we have, when you add the x1, negative x1, gone, right? The x1 variable is gone, is eliminated. When you add the two equations, the left-hand side becomes twice x2. The right-hand side, 0 plus 8, which is 8. So that means when you add, you can eliminate one variable, which is x1. And you get an equation of only involving x2 variable. So it's much easier to solve because I have only one variable. Then I divide two both sides, get x2. So let's divide two both sides of the equation. Then the left-hand side becomes x2, the right-hand side becomes 4. So once you get x2, and now you substitute the value of x2 into either one of the two equations. And so if x2 is 4, what is x1? So let's say I substitute 4 into the first equation. The first equation, so that means x1, because x2 is 4. In order for the first equation to be true, x1 has to be negative 4. So yeah, I subtract negative 4 from this equation, I get x1. So now I get x1, I get x2 both. And then because I found x2 first, right? From x2, I can use either one of the two equations to get the other variable. So we found a unique solution But can I claim that it is a solution? So let's remember this. X1 is -4, X2 is +4. Let's check. The solution I found is X1 is -4, X2 is +4. So you substitute the -4 into X1, +4, right, to replace X2, and then you immediately get 0. Okay, that means first equation is true. And then again, I want to check whether this is a solution for the second equation. So if X1 is -4 with a negative sign in the front, it's going to be +4. And X2 is 4, right? So I'm going to check. Yeah, so +4 plus 4 is 8. That means they also satisfy the second equation. So we have found this is indeed the solution, a unique solution. Yeah, that's the only solution for the system. So far, have you noticed? It's possible a system has no solution, right? In the previous case, no matter what value of x1, x2, they will not make the system a true statement. So this system just contradictory to itself, right? So that means this quantity cannot be both 0 and 5. If it's both 0 and 5, that means 0 equals 5, right? So that means no solution. And also it means sometimes we have a unique solution, like the second example shows. But can we have more solutions? So if we look at some other examples, if I have still two variables, let's say x1, x2, I have, and then suppose I have 4x1, 4x2, I have again two systems. And let's try to solve it. When we try to solve it, again, it's always convenient if you label the first equation, second equation, right? This is our first equation, second equation. Yeah. So, and what do? We like to simplify it by eliminating some variables because we don't want to have two variables in one equation. Hopefully we can get only one variable in an equation so that we can get value of a variable. So we compare the coefficients. See the first equation, if you multiply the first equation by 4, so the first equation times 4. That means each term of the first equation times 4. What do I get? The first equation becomes 4x1, 4x2. 4 times 3 will be 12. So it becomes the second equation. That means the first equation is just the same as the second equation. You see, after we do a scaling of the first equation, like 4 times of the first equation becomes second equation. That means second equation can be reduced to the first equation as well if you divide the 4, right? So these two equations are the same equation. So you have one equation for two variables. So let's also, because this is the same as second equation, that means if I subtract the second equation, what happens? And we will get 0 equals 0. So first equation times 4 is the same as second equation. If you do a subtraction, So you will get 0 equals 0. So that means it's always true. This system has infinitely many solutions. That means no matter, that means any x1, x2 that is on the first, that any value for x1 and x2, as long as they satisfy the first equation, they will satisfy the second equation. That is how many. So how many will satisfy the first equation? Every point on this line, right, will satisfy that equation. That means every point on this line will be a point on the other line because they are the same line, they overlap. Okay, so this is a third case that we see infinitely many solutions. So to summarize, that although the three examples involve only two variables, right? They are systems of two variables. But this phenomena can be generalized to n variable systems. So if you have a system of many more variables, and we will discover in the future that there are actually three cases. No solution. There's no solution to the system, or one solution, one and only one solution. That means a unique solution. So we can say only one solution. And another case is infinitely many solutions. Yeah, just three possibilities for any system of linear equations, no matter how many variables. Yeah, so you just saw the example, three examples of linear systems involving only two variables. But in general cases, we also will see that three cases are quite typical for general linear systems.